Okay, it's 7 p.m., so let's go ahead and get started today. All right, good evening, everybody. How's everyone doing today? It's been a while since I've seen you guys. We didn't really have a lecture at all last week because we had a midterm on Monday, and then Wednesday I had internet troubles. So it's been a while. So I apologize again for what happened on Wednesday. So you know, I always like to have these kind of live sessions just because, you know, it's a lot better when you guys can see it kind of real time and you can ask questions, and because you know it's kind of easy for me to kind of lecture just to my laptop like this, but then, you know, without your guys' feedback, it's really hard for me to know, you know, what things are going over well and, you know, what things, you know, I could explain better. So, you know, I definitely don't plan on doing that more in the future. You know, I definitely prefer these a lot more, but, you know, hopefully, you know, the internet stays stable for the rest of the semester so that we can continue to have these at our normal time. So with that said, today we're going to start something new. So we're going to jump into kind of the final topic of the class, which is turbulence. So turbulence is a really big subject, and we're only going to cover it for 3 lectures. So, you know, we're not going to be able to cover all too much, but we can at least cover the main concepts, which is kind of my goal. Right? Before we do that, let me just talk about the midterm really quick. So you guys did really well in the midterm. So the average was 42 out of 50. So you guys did really well. So the solutions for the midterm are online already, so you can definitely check that out, and definitely check out the feedback that I have that I posted online too, just so you know, just so you kind of know. So just real quick. So on the feedback that I gave, if you got the problem completely right, I didn't really write anything. It's basically only whenever I was going to take points off that I wrote something. So. Definitely check that out. You know, at least, at the very least, just from the perspective of you know, making sure I added up everything correctly, so you got all the points. If you have any questions about, you know, the midterm or you know, the grading, then definitely let me know. Okay. Okay. So before we start today, are there any questions just on the midterm or anything? Okay. So if there's no questions, let's go ahead and get started today. So the final topic that we're covering in this class, like we said earlier, was turbulence. Okay. So turbulence is a very rich area of study. So it's kind of amazing, you know, something that's been studied for so long, and there's so many research groups. I think, you know, a lot of universities have at least one person that does turbulence to some degree, and yet there's still so much that, you know, we have yet to learn about turbulence in general. Okay? But turbulence, you know, specifically for certain kinds of people who do fluid mechanics, turbulence is like really serious business. So it's almost like a religion to them. So, you know, there's even a pope. See, this guy's the Pope of Turbulence. Okay, so he even wrote the Bible. This is kind of like the Bible of turbulence here. So it's you know, very serious. You know, lots of people take it very seriously. At, you know, where I went to grad school, there was they had even a center for it. So they call it the Center for Turbulence Research. They call it CTR, and it was run by kind of these faculty where they're very tough on you if you ever present anything on turbulence. So basically, whenever we brought in guest speakers to speak, and they're speaking on turbulence, you know, I always kind of joke, said like, oh man, the turbulence mafia is going to get them, because they always, you know, ask really tough questions. So, you know, luckily, or maybe not so lucky for you guys, I'm not a turbulence person at all. So I'm one of those kind of fluid mechanics researchers who study something so niche that it's actually mostly laminar. So my understanding of turbulence is mostly kind of a textbook understanding, I guess you can say. So you know, I know what I've read in the textbook, and I know what I've taken in class, but, you know, I haven't done a lot of work in it, which is really strange, because actually a lot of flows actually end up being turbulent. Okay? So just as an introduction, so kind of building on what we talked about last week, we know that turbulence occurs kind of as a result of instability in the flow. Okay, so onset of turbulence. is triggered when small instability or small disturbances of the flow, they grow rapidly over time. And then as we found out last week, that the kind of the onset of turbulence, or the way that turbulence is always triggered, is that there's always some kind of instability in the flow. Okay. So once you have an instability, and once that instability grows, then you kind of get this chaotic flow state, and that's kind of what we know as turbulence. Okay. And as we kind of discussed before, like one of the conditions where you get this, you get these instabilities that grow, are when the Reynolds number is really high. Okay. So even though for most of this class we've kind of avoided the topic of turbulence, just because it's really hard to analyze turbulent flows, but that's it's not kind of fair to kind of practical flows and interest, because actually for a lot of flows that engineers deal with in practice, you're going to have some turbulence flows. Okay. So a lot of the situations that we went over in this class, like low Reynolds number flow or lubrication flow, or even a lot of the research that I've done, which is in blood flow, those are very niche situations where you have laminar. But most practical things, like you think of flow over an airfoil, or any kind of atmospheric or ocean flows, or even flow just in pipes that line your line buildings, most of those are going to be turbulent. So kind of just taking from a famous movie quote, you can dread it, you can run from it, but most of the time turbulence still arrives in one way, shape, or form. So whether you like it or not, and most people don't like it, you're going to have to deal with turbulent flows if you're going to do any kind of fluid mechanics work in practice. Okay. So with that, I kind of want to dispel just kind of one kind of misconception. So when a lot of people think of turbulence, they think of just kind of pure randomness, but turbulence it's not pure randomness. Okay. So it's not like when you have turbulent flow, then everything just kind of, everyone just kind of does whatever. So there's still some rhyme or reason to, to turbulent flows. Even though, it does seem very chaotic, it does still obey the laws of, say, like conservation of mass and conservation of momentum. Okay. And so because of that, because turbulent flows, they do still obey some basic physical laws. And even though it's really hard, we can still, to some degree, do some analysis and do some predictions in order to do some, really useful engineering work. It's actually, just from just from my point of view, despite everything that we don't know about turbulence still, and despite all the many assumptions that we have to, like really heavy assumptions that we have to make, we can still do a lot of really amazing things with turbulent flows. Like even just, just the fact that we have airplanes that fly in kind of very turbulent conditions. It's really kind of amazing what we've done, despite, this field kind of not really advancing as far relatively compared to some other fields. Okay, so are there any questions on this before I turn the page? Okay. Okay, so let's just talk generally first. So let's talk about just some general characteristics that that you would expect from turbulent flow. Right? So the first thing that you'll notice about turbulent flow, which will be kind of a you know, a prevalent theme as we go about the next couple of weeks, is this idea of fluctuations. Okay. So for any flow quantities that you can think of, so the main ones that we've been dealing with are things like velocity and pressure. All of those are going to have kind of random, unpredictable fluctuations. Okay. And so one other thing that that we're not really going to cover in this class, but it's still important for turbulent flow, is temperature. So we haven't really dealt with temperature as a flow variable, but for a lot of situations, that's important. Okay. Okay. And so we're actually going to, have an expression for those fluctuations. Okay. Once we start doing some analysis. Okay. So the other thing is non-linearity. Okay. So remember, in turbulent flow, one of the biggest defining characteristics is that the Reynolds number is really high. So when the Reynolds number is really high, then all those terms on the left-hand side, which are our convective terms, so our u du dx, our v du dy, and our w du dz, those terms are highly unlinear, non-linear. So because our Reynolds number is really high, then those terms are going to be really prevalent. Okay. All right. So number 3 is vorticity, which is what we covered 2 weeks ago. And so what tends to happen in turbulent flows is you have these kind of really small pockets of spinning flow, or kind of small pockets of vorticity or circulation in the flow. Okay. And so often what we call these in turbulent flow is eddies. Okay. Okay. And so we're going to talk a lot about those eddies, and how that affects things like the energy in a turbulent flow. Okay. Okay. So the next thing is dissipation. Okay. And so because we have this really chaotic motion with all these kind of pockets of local vorticity, you're going to have these pockets where the velocity gradient is really high. So in other words, when the velocity gradient is really high, then our viscous dissipation is also going to be really high. Okay. And so when I say dissipate, what that means is that turbulent flow is going to take kinetic energy, which is kind of the energy that's associated with the motion of the fluid flow, and it's going to convert that to heat because you basically just have viscous friction that's kind of converting that to heat. So very similar to, you know, when you rub your hands together, they start to feel warmer because the kinetic energy of them moving is converted into heat. And in fact, you know, turbulent flows have much higher dissipation than laminar. So if you want to kind of sustain a turbulent flow, you need kind of a constant source of energy to always drive it, more so than laminar. And then the last one is diffusivity. Okay. And so this one's, you know, probably the most important for a lot of practical applications, that when you have turbulent flow, because you have this kind of chaotic motion, it really enhances things like mixing. So, you know, if you're talking about this from like a heat transfer perspective, you know, those who do heat transfer work know that if you have turbulent flow, then heat will mix a lot easier. Where if you have kind of a hot surface here and a colder fluid, the surface will lose a lot more energy if your flow above it is turbulent. Okay. So things like energy and momentum mix more efficiently. Okay. Okay, so those are kind of the 5 kind of main features of characteristics of turbulent flow. That's, I think, kind of, you know, good to kind of ground your intuition behind, okay? So if, with these 5 things in mind, then we can kind of start to kind of talk about some of the analysis in mathematics. Okay? Are there any questions on this? Okay. So with those characteristics in mind, you know, it might be useful to kind of have you know, a slightly more nuanced definition of turbulent flow, because right now our only definition of turbulent flow is just flow that's really chaotic and turbulent when Reynolds number is high. Okay, so we can do a little bit better than that. Okay, and I'll say just a little bit better. Okay, so another kind of definition for turbulence is that it can be defined as a dissipative flow state characterized by nonlinear fluctuating 3D vorticity. So basically, you know, we took every single word or every single characteristic and we kind of just put them into a single sentence. Okay. So, you know, hopefully after we kind of go over the next few lectures of turbulent flow, then this will hopefully be a more satisfying definition than just chaotic and random flow that occurs with Reynolds numbers really high. Okay. Okay. So let's get into some of the analysis. Okay, so before we do that, we kind of have to kind of make some definitions and kind of set some ground rules. So this is kind of the almost like the kinematics of turbulent flow, I guess. Okay, so let's talk about fluctuations and time averaging. Okay. And so because you know, turbulent flow is characterized by these you know, fluctuations, oftentimes, you know, the way that we characterize these mathematically is we kind of borrow from the literature on things like random processes or stochastic processes. Okay. And so the whole concept of a random variable is you know, is going to be prevalent here. Okay. Okay. So when I say our variable is random, that means it doesn't have kind of a fixed value. So it's not like, you know, normally when we do a problem, we say the viscosity has this kind of fixed value. But if we say the viscosity is random, then basically what that means is that, you know, every time we observe it or every time we evaluate it, it's going to have a different value. Okay. It's not that the value itself is changing. It's just that we don't know enough about the value in order to kind of pinpoint one thing. So like kind of every time we observe it, we get kind of we get something different. Okay. And so that idea is going to be kind of prevalent in turbulent flow. Okay. But we're not going to get into too much of the stochastic kind of processes because that can go really deep as well, because we need to understand things like correlations and probability density functions, which, you know, is kind of beyond what we can do in kind of 3 lectures. Okay, but I think it's kind of important just to kind of understand just you know, where it's coming from and, you know, how these things are kind of described in general. Okay? So typically when we talk about turbulent flow, we apply what's called the Reynolds decomposition. Okay. And so what this is we're going to take our flow variables and we're going to break it up into 2 parts. Okay. Okay. So let's just take the velocity for some instance. So we'll say that our total velocity is going to be equal to the sum of u bar plus u prime. Okay. So this right here is going to be our total total velocity in this case. But you can apply this to anything. So I'm just doing velocity just because that's the one we'll be mostly working with. Okay. So I'm going to use this overbar notation to denote the mean. So this u bar right here is going to be our mean value. So if you kind of, you know, look at this this velocity for a long time and you kind of average it over a long period of time, that's what you get. That's what you get. Okay. So the important thing for the mean is that this contains no fluctuations. So it's a you know, a deterministic variable. Okay. Okay. And then this u prime right here, these are kind of the random fluctuations that we'll experience. Okay. Let me box this. And so kind of the key here is going to be random. So we're going to use, typically what's used is we use random variables to describe those fluctuations. Okay. So this is, you know, if you kind of think back to last week, this isn't too different from how we formulated our instability problems. Because when we did our instability problems, remember we broke up our flow quantities, which was mostly velocity, into a background flow or a base flow and the disturbances. Okay. So this idea of kind of additively kind of decomposing these things is something that's, you know, quite common in fluid mechanics, and it does help with some of the analysis to a degree. Okay. All right. Any questions on this? Okay. So visually, it might look something like this. So let's say that, you know, you're designing a system that has turbulent flow. Okay. And let's say that you get kind of a noisy waveform that looks like this. Okay. So if we break this up into a Reynolds decomposition, we might get 2 things that look like this. So we might get a mean flow that's kind of absent of that doesn't have any you know, fluctuations at all. So you can see there's kind of that background wave. And then you also have kind of the random fluctuation. So this is kind of u prime right here. Okay. So that's just kind of a way just to visualize it. Okay. Okay. So let's talk about this u bar for a second. Okay. So this U bar is simply the mean. So, you know, we define it in terms of, you know, basically a time average, okay? And so typically the way that you would compute it, or at least kind of the mathematical definition of it, is given by this. So we utilize basically the mean value theorem, where we integrate our velocity in time from 0 to up to some up to some time point capital T, and then we divide by that. Okay. Meanwhile, our U prime here, remember U prime is a random variable. Okay. That means basically every time that we observe U prime, it's going to change values a little bit, okay? But, you know, one important property of U prime that is kind of not illustrated well here is that the fluctuations are going to be 0 in the mean. So if you take your fluctuations and then you take the average of it, or you take the overbar, then you should get 0 there. Okay? And so the idea with this is that these fluctuations, they don't contribute anything to kind of the bulk motion of the flow, at least in a time average sense. But locally, they are going to cause some differences. Okay, but in kind of the bulk average motion case, you know, they're not going to make a difference. But there's these kind of think of these as just kind of random fluctuations that happen, but they don't, you know, drive kind of the flow forward. All right, any questions on this? Okay. Okay. So even though the average value of those fluctuations are 0, what's going to be really important is that the square of those things are not going to be 0. Okay. So if you take your fluctuations and you square it, and you take the average of it, okay, what's going to happen is that you're not going to get equal to 0. Okay, and in fact, what you're going to get, because it's a square, you're going to get something that's going to be greater than 0. Okay, and so what this is called, which is going to be important once we start talking about kind of the kinetic energy of these fluctuations, is this is known as kind of the root mean square value, or RMS value, for the fluctuations. Okay. Okay. And so, you know, this kind of overbar operator is going to be something that we're going to use a lot. So let's talk about just some properties. Okay. Okay. So I'm just going to kind of list them all out, and then we'll talk about it. Okay. So if you have two quantities and you take the overbar of them, okay, overbar is commutative with addition. So this is going to be equal to U bar plus V bar. Okay. Another thing you can do is you can multiply by a scalar. So if A is just some number, if you multiply by if you take kind of the overbar of that, since A is just a constant value, you can just kind of take it out and you just take that thing. Same thing with derivatives. So let's say we have du dx. Okay. You take the overbar. Okay. You're going to end up with du bar dx. Okay. And then same thing with integration. So you can take integral of u dx and you integrate it, and then you get integral of u bar dx. Okay. Okay. So then once we're kind of doing some derivations later, these properties are going to be important to know. Okay. Okay, so those are all the properties which are commutative with the averaging. So let's talk about two things that aren't. So if we take the fluctuations of something, or we take the prime, that's not commutative with averaging. So we have u prime bar. Okay, this is not going to be the same as u bar prime. Okay, so it's a little subtle here, but you can see that on the left side, the bar is kind of outside of the prime, and that's not the same by taking the bar kind of inside. So those two are not equivalent. Okay, and kind of most importantly, which is kind of implied by the definition of RMS up here, that if you multiply two quantities and then you take the overbar, you can't just break that up. So you can't just say u times v bar. It's not going to be the same as u bar times v bar. Okay. So these guys are not the same. So if you take kind of the bar of two quantities, then you kind of have to keep them together. You can't kind of separate them into separate quantities. Okay. Okay. Any questions on this? Right. So the question is, what does the bar mean? So the bar is basically just going to be a time average. So basically, whenever I have a bar, that means I'm averaging it over time. Okay. Because a lot of times turbulent flows, they have all these fluctuations. So in order to kind of make sense of it, a lot of times we need to take the time average of certain things, just so we kind of get kind of the bulk motion behind that. So that's what the bar means. Mm-hmm. All right. So I have a question of how do we get u prime? So u prime is just the definition of how we're going to define the fluctuations. So remember, the fluctuations are just kind of random things, or just kind of random ways for the velocity to kind of go up and down. So it's we don't really derive it. We just kind of say that this is just a property of the flow. It's something that we're going to want to solve for in the end. Okay? So the reason I kind of have these properties like this is that later on, what we're going to do is that we're going to plug in basically this guy right here, this kind of Reynolds decomposition, and we're going to plug that kind of directly into Navier-Stokes. And then what we're going to do is we're going to take an average of that and kind of apply some of these properties to kind of simplify it as best we can. Okay. Okay. So now let's talk about some turbulence, actual turbulence concepts. Okay. So let's talk about turbulence production and the energy cascade. And so because turbulent flow, they have all these random fluctuations, what tends to happen is that you have eddies or flow structures of many different sizes in the flow. Okay. So just to kind of draw a kind of a simple picture, okay. And to kind of emphasize this this fact that these flow structures, the eddies, can be very many different sizes. So you might have some eddies that might look like this. Okay. So if you say that if we say that this is a pipe of some diameter d, we might have some flow structures that are kind of the same size as d. Okay. So we say that this is kind of a large eddy. Okay. We say it's large because given the length scale in this problem, it's kind of as big as it can be. Okay. But then kind of from that large size, you can also have lots of eddies of smaller sizes. Okay. So you might have like a medium eddy, a smaller eddy, maybe another medium eddy, maybe another big one. Okay. So, it doesn't really look like exactly like this. So if you kind of look at turbulent flow in your pipe, you're not going to see these kind of spinning flows, but at least momentarily and for like some brief instances, you do have kind of these flow structures that are of various sizes, and that's going to be really important. Okay. And so what's going to be really important, you know, for turbulent flow, because, in laminar flow, we don't have this, because in laminar flow, we just have flow that just goes in one direction. So there's just a single length scale. And, there's a lot of kind of simplifications that we can do, kind of as we've seen for, the last 15 weeks, okay? But for turbulent flow, what makes it so difficult to analyze is that you have all these different flow structures of different size. And even worse is that when you have all these flow structures, what's going to happen is that they're all going to interact with each other. Okay. And so when these flow structures or these eddies interact, they're going to exchange a lot of stuff, right? But kind of the most important thing that they're going to exchange, or in most cases they're going to transfer, is their kinetic energy. Okay. Okay. And so the nature of that energy transfer is one of the really core concepts of turbulent flow. Okay. Okay. So first, let's go over another definition. So let's go over turbulent kinetic energy. Okay. So turbulent kinetic energy is often called TKE. Okay. So what turbulent kinetic energy is it basically defines, how much energy is in the fluctuations. Okay. So it's given by this formula here. So it's given by 1/2 u prime squared average plus v prime squared average plus w prime squared average. Okay. So there's a whole host of methods that really base things off turbulent kinetic energy. So we're not going to look at those methods just because it's kind of beyond the scope of what we can cover. But I think it's important just to know what it is. Okay. Because this idea that these fluctuations will have energy, or these eddies will have energy, is something that's important to know. And the way that you kind of characterize that energy, you say how much energy does this eddy have. What you can do is you can measure basically how fast it's going and what its velocity is, and basically use that to compute some kind of kinetic energy. Okay. All right. Any questions on this? Okay. Okay. So, we know that turbulent flow is comprised of all these flow structures of different sizes. And so one really important concept is that, the eddies or the flow structures with the largest size, these often can't really be sustained for that long. Okay. And so, in fact, what tends to happen is that these larger eddies, because their position is not stable, although it's stability in kind of a different sense than what we talked about last week. So, because they're unstable, what tends to happen is that the kinetic energy of those large eddies, you can imagine that you have a really big eddy like this, okay, and then once it breaks up, all that energy has to go somewhere. And so, what tends to happen is that this bigger eddy kind of breaks up into a bunch of smaller eddies. Okay. And so one thing that you can talk about, or one thing that might be interesting, is asking how long does a large eddy last. So if we have kind of a large eddy, so how long is that going to last in this turbulent flow? Okay. So so that question is answered by defining what's called the turnover time. Okay. Okay. So this is not a formula, really. So it's I'm giving it just kind of this tilde here. So this is just kind of an approximation. So you can kind of think of it as like kind of an order of magnitude, calculation. Okay. So the turnover time, or the amount of time that a large eddy lasts, the way you can compute it is you can compute, you can take L and divide by U. Where L right here, this is the length scale of the flow. Okay. And this U right here, this is a characteristic mean velocity. Okay. So if you have a flow which has some length scale and some mean velocity, you can compute roughly on the order of magnitude how long a large eddy lasts. Okay. So when a large eddy breaks up into smaller eddies, one way that you can think about it is that that large eddy is kind of taking its energy and then transferring it into smaller energy, into the smaller scales. Okay. And so, one thing that you might be interested in is, what's the rate at which this this transfer occurs? Okay. Okay. So that's going to be computed by this. Okay. So let's take the velocity fluctuation. And then what we're going to do is we're going to perform what's called an outer product. Okay, so that's what this term means. Okay. So you're going to take an outer product of the fluctuation velocities. And then what you're going to do is you're going to do kind of a scalar matrix product. So that's what these kind of two, that's what this colon means. Okay. So kind of the way that I explain this, I would explain this is that everyone's kind of familiar with a dot product. So a dot product between two vectors gives you a scalar. So there's kind of a tensor version of this, or where you take two matrices and you multiply them in a certain way, and you get a scalar out of it. So that's what this is. So this is, the real name is kind of a double scalar product. Okay. Okay. And if you take the double scalar product with the gradient of the mean velocity, that tells you the the rate at which this energy transfer occurs. Okay. So this is a really, obviously this is a really complicated mathematical beast. So you're kind of catching a glimpse of why turbulence is so hard to analyze. Okay. So, for many practical cases, you're not going to evaluate this unless you're doing a very, very expensive simulation called DNS, which we'll kind of mention next week. Okay. But kind of the important thing for this is that, this term right here. So this term, it's going to come up again quite a bit, especially in our equations. So this kind of outer product of two fluctuation velocities, this is what's going to be called our Reynolds stresses. My cat is still hungry, even though it just ate literally an hour ago. So, you know, we're going to spend a lot of time talking about these Reynolds stresses because it's, you know, it's kind of unintuitive at first because it's, you know, we have these two velocities, right? So we have, you know, u prime and v prime. So they're just two different components of the fluctuation velocity. And so, you know, by taking this kind of magical outer product here, somehow we get something that's like a stress, you know, but stress is, you know, usually we think of things like the viscous stress or things that can actually, you know, affect the momentum of our fluid, right? So how can velocity itself, you know, and velocity of the fluctuations actually be something that can actually affect our momentum and apply kind of an external force on our flow, right? So that's kind of some questions that we're going to answer kind of both today and on Wednesday. Okay. And so what this term kind of overall defines is this term kind of defines the interaction between our turbulent fluctuations and our mean flow. Okay, I'll kind of write that down on the next page. But are there any questions on this page before I turn it? Okay. Okay. So the important thing that I want you to notice, you know, compared to a lot of other terms that we've seen in this class, is that term right here, okay, this Reynolds stress, kind of a double scalar product with the velocity gradient. There's no viscosity here. So this process of, you know, energy transfer between kind of the large eddies to the smaller ones, this is a completely inviscid process. Okay. And so what does this mean for dissipation, right? Because remember, one thing that we said was that turbulent flows are dissipative. And, you know, for dissipation to occur, you need some kind of viscosity. So if we have this kind of, you know, energy transfer from the larger scales to the smaller scales and viscosity is not even involved, you know, where does viscosity even come into this? Okay. And so the answer to that is viscosity doesn't really enter into a turbulent flow until you get to kind of the smallest flow structure. Okay. Okay. And so what this means is that, you know, the turbulent flow, it's not going to lose any kinetic energy from the larger scales. Where it actually loses energy is actually from the smallest scales. Okay. Okay. And so how do we know when we've reached the smallest scales, right? So we know what kind of the big scales are. So we know the big scales are kind of on the same order as kind of the geometry of our flow. So where are the smallest scales? So how small is small, right? So to kind of guide us here, you know, we can use something that we've used a lot before, which is the Reynolds number. So we know that the Reynolds number you know, it's the product of some velocity and some length divided by the viscosity. Okay. Okay. And so let's say that L right here, this L is going to be the length scale of the smallest, or the kind of the diameter of the smallest eddy. Okay. And so when this, you know, when the eddies get small enough such that the product of the velocity and the diameter of the smallest eddy divided by the viscosity, that equals 1, that's going to be the smallest eddies that you'll see in turbulent flow. Okay. And so depending on the velocity of your mean flow and depending on the viscosity, that's going to change the size of the smallest flows. Okay. Right. And so, you know, if we kind of put everything together, you know, if you have turbulent flow, we know that turbulent flow is going to consist of flow structures of all different sizes. And constantly what's happening with these different sizes, that the big flow structures, the big eddies, they're going to be transferring energy from themselves into eddies of smaller size, just from the fact that, you know, the big eddies we know are going to break up. Okay. And so, you know, we have this kind of constant transfer of energy where like large scale flow structures will form. Those will break up into smaller eddies, and those will break up into even smaller eddies, and those will break up into smaller ones until you reach kind of the smallest scale. And then once you reach the smallest scale, then that energy is basically dissipated by viscosity. Okay? So this whole process of you know, energy being transferred from the largest scales to the smallest scales, this is what's known as the energy cascade. Okay. And so just a little bit of history, you know, the first person to kind of formalize this into a theory was a mathematician called Lewis Richardson, and that was in 1922. Okay. Okay. Any questions on this? Okay. So remember, we kind of have two distinct processes here. So we have a process of bigger eddies breaking up into smaller ones, okay? And that's an inertial process. Okay. And then the other thing that you have is kind of the viscous dissipation of the smallest eddies. And this is, of course, viscous driven. Okay. Okay. So those are kind of the two processes that are kind of going on at the same time in turbulent flow. Okay. So at first it might seem that these two aren't really connected, so because one is driven mostly by inertia and the other one is driven by completely by viscosity. And you know, kind of we usually separate those two things, but these things are linked because both of these are kind of energy processes, right? Because the first one you have kind of a transfer of energy from the large eddies to the small ones, right? But because, you know, things in turbulent flow, they tend to be what's called kind of quasi-static. You can't have kind of an accumulation of energy at kind of one scale or the other. Okay, and so what tends to happen is that the rate at which, you know, this, even though we say that this process, the physical process of this being big eddies breaking up into smaller ones, that's the physical mechanism of that is purely inertial. Kind of the rate of that is kind of determined by this. Okay? And so what that means is that you can't have the rate at which bigger eddies break up into smaller ones. You can't have that faster than than the viscosity is dissipating energy in the smaller ones. Okay. So kind of the first thing that you determine in turbulent flow is how quickly do our small scale structures dissipate energy, which is a viscous process. And then once that's determined, that'll tell you, how quickly your big eddies can break up. Okay. Okay. So, another term for this, today's kind of be mostly just concepts and kind of terminology. Another way that we can talk about kind of the this breakup is that we can say that once the bigger eddies break up, then this produces turbulent kinetic energy. Okay. All right. Any questions on this before we get into Kolmogorov? Okay. And so next we're going to talk about a very influential researcher in turbulent flow. So his name is Kolmogorov. So keeping along with the theme from earlier, Kolmogorov, he can kind of be thought of as like turbulence Jesus. Okay. So a lot of his work has been kind of very influential on how we think about turbulence today. Okay. So a lot of his work he kind of built on kind of the work of Richardson of this kind of energy cascade. So Kolmogorov was kind of very interested in that and kind of saying what else can we learn about this energy cascade. Okay. Right. So kind of the first thing that he proposed was that these kind of the smallest eddies that you see in turbulent flow, which are really important because those are the ones that dissipate energy. If you characterize those things, then he says that these eddies are both isotropic and homogeneous. Okay. And so by doing that, he said that there are basically two main parameters that kind of drive turbulent flow, okay? Or two main parameters that you need to be concerned about, okay? The first is the viscosity of the fluid. Okay, so that's given by nu. Okay, so that one we know. Okay, and the next one is the rate at which the large eddies, supply energy to the smaller ones. And then we'll give this the variable epsilon bar. Okay. Okay. So from these two parameters, we can define a length scale and a velocity scale. Okay? So let's say that we have this eta. So this is going to be nu cubed, all divided by epsilon bar, okay, to the 1/4 power. Okay? So this right here is our Kolmogorov length scale. Okay. And then we have UK, which is our Kolmogorov velocity scale. This is nu epsilon bar to the also to the 1/4 power. Okay. And so what Kolmogorov says is that because epsilon bar, which kind of defines that inertial process that we talked about earlier, it doesn't depend on the viscosity. So these two are completely kind of independent parameters. Then what tends to happen is that if you change the viscosity, then what that'll do is that it'll affect kind of the size of the smallest eddies. Okay? So it'll basically kind of reduce the size or increase the size. Okay? And so just to give you kind of a sense of scale, so if you consider things like oceanic flows or flows that happen in the atmosphere, these have kind of length scales that happen on the orders of kilometers. So you might have eddies, they might not persist for a long time, and they might not form like a whirlpool or a hurricane, but they have length scales which are on the orders of kilometers. Okay? But because of how fast and how high those Reynolds number are, and how small the viscosities can be, their Kolmogorov length scales, or the length scales of their smallest eddies, can be on the orders of millimeters. So you go from things that are kilometers down to like millimeters. So there's a huge range in between the largest flow structures and kind of the smallest ones. So it's kind of hard to kind of fathom that, and that's part of what makes modeling turbulence so challenging, where you need to not only model things that happen on a really large scale, but you also need to model things that happen on the smallest scale in order to be completely accurate. Okay? So computationally, what this means is that you need to have a ton of points in your grid. Okay? So if you're running things like a CFD, like a finite volume or finite element, you need to have elements that are small enough to basically capture the Kolmogorov length scales, but you need to have so many of them in order to capture kind of the biggest scales, and that's kind of one of the biggest challenges of modeling turbulence. Okay. All right, any questions on this? Okay. Okay, so now that we have kind of a better idea of at least how we can define or how we can scale the smallest scales, this kind of gives us the two ends of our spectrum. Okay, because remember, turbulent flow, we're characterizing it as a collection of flow structures of many different sizes. So now we know the smallest size. So the smallest size, we can define it in terms of eta, which is what we did before. And we can say that the largest size can be L, so that's kind of the length scale of the kind of the mean flow itself. So that could be like the diameter of your pipe, for instance. Okay. But in between that, we have a ton of other length scales, right? So in between kilometers and millimeters, we have the meters, the centimeters, everything that's kind of in between. Okay. And so that's this kind of range of scales has a special name. So we call this the inertial subrange. Okay. So it's called the inertial subrange because if we think about, physically what's happening with the eddies of these sizes, if we consider some lambda that's in between the Kolmogorov length scale and the length scale of the flow, then what's happening is that there are eddies of these sizes, and those are eventually breaking down. Okay? And remember, the breakdown of larger eddies into smaller ones, that's purely an inertial process. So that's not driven by viscosity at all. So in this subrange, what we say is that eddies in this range of this size range are breaking up into smaller eddies. Okay. Okay. And that process is purely inertial. Okay. Right. So then now we're kind of getting into kind of the Kolmogorov's kind of most influential work, which is known as the -5/3 law. Okay. And so because we have this breakup of length scales, one kind of way to describe this is instead of using kind of a description that relies on kind of what we call like length and time, one way that you can also do it is you can describe it in terms of a spectrum. Okay. Okay. And so what the energy spectrum will tell you is it'll tell you how much energy is currently in an eddy of a particular size. Okay. So the energy spectrum is a way to define energy of flow structures of various sizes. Okay. So one of Kolmogorov's most important works was kind of defining this energy spectrum. Okay. So what he said was that E, where this E is the energy, the energy in a turbulent flow is goes as epsilon bar to the 2/3. Okay. Remember, epsilon bar, that's the rate at which energy is transferred, and then this kappa to the -5/3. Okay. And so kind of the important parameter here is kappa. So this kappa here is the wave number of the flow structure. Okay. And then wave number is nothing more than just going to be 1 divided by lambda. Okay. So basically what that is that you take, once you have the size of the eddy, and that's given by that lambda, what you're going to do is you're going to invert it, and that's going to give you kappa. Okay. And so what Kolmogorov found out was that, the energy is basically proportional to that kappa raised to the -5/3. And so what you can do is you can basically form a plot of, how much energy is kind of located within these, these different length scales, and it's going to follow this -5/3 law. Okay. Okay. Any questions on that? Yeah. So I know a lot of this is kind of really dry and kind of theoretical, and we are going kind of fast. I think originally I had planned for turbulence to take up at least 2 weeks, 2.5 weeks. But because of the situation and stuff, then we're kind of getting the Spark Notes version. So we're getting kind of a lot of concepts kind of thrown together at once. So definitely don't be shy if things aren't making sense. Then definitely let me know, because it's a lot of stuff, I know, and it's very, very different than I think the stuff that we've done before. Okay. So when you Google Kolmogorov's hypothesis, you'll probably come up to a plot that looks like this. Okay. So the y-axis of this plot will be the logarithm of the energy, okay. And then the x-axis is going to be the logarithm of k, and then what you're going to see is a graph that looks like this, where you have this region right here, given by a straight line, where the slope of this line, which I didn't really draw it that well, is going to be -5/3. Okay. And so these 2 points, which I've marked off with the dotted lines, these are really important parts. So remember, K is the the inverse of the flow structure size. So that means the flow structures with the largest size are going to be on the left here. Okay. So this is going to be 1/L. Okay. So the flow structures with the largest size are given by that. And then on the far right side here, we have 1 over eta, or 1 over the smallest length scale. Okay, and so what this graph tells you, it basically tells you how the energy is distributed among the different length scales in turbulent flow. So you can see that most of the energy is still going to be given by the large flow structures, which makes sense because these are kind of the largest ones. But then, through time, these large flow structures are going to break up, and then it's going to distribute that energy among the smaller length scales. Okay? And so you kind of have this kind of -5/3, distribution where, the amount of energy kind of decreases as you get to the smaller ones. Then once you get down here, remember, this is when viscous dissipation takes place. Okay. And so the reason, this plot is so famous is because when Kolmogorov first came up with this theoretically, like many, famous researchers, everyone thought he was a crazy person. But later on, a lot of experiments were run with different, researchers with different groups kind of independently. And through their measurement, they were actually able to confirm this -5/3 loss. So, you might see plots online that have kind of a lot of data points like this that kind of represent, the experimental data that confirms this. So this is kind of one of those things which, people thought was, he was a crazy person, but, he was actually right. Okay. And so, the last thing that I kind of want to leave you with is kind of an analogy that I like to think about turbulence. Okay? Because remember, the theme for today is that there's kind of 2 separate processes that happen in turbulence. You have large eddies, large flow structures that are on the same order of size as the flow itself. So eventually those break up, and then those, and by breaking up, they take their energy and they transfer it to eddies of smaller scale. Okay? And then those break up, and they transfer energy to the smaller scales, eventually until you get to the smallest flow scales, which kind of dissipate the energy. And once the energy is dissipated, it basically turns into heat, and then you basically throw it away. Okay. And so one way that I like to think about this is I like to think of a row of stick people, okay, of progressively smaller size. Okay. So over here, you have your length scales of the largest size. So this could be like Shaq. Okay. And then down here is me, okay, because I'm a tiny person. Okay. And so, this is kind of this serves as kind of a good analogy for turbulence, because we know that the large flow structures can't dissipate energy. So let's say Shaq kind of has a bucket of some fluid that he wants to throw out. So he has like some bucket of trash. Okay. Oops. Okay. So that's his kind of bucket of trash. Okay. But he can't throw it away because the trash can is over here. Okay. And he's kind of too big to kind of reach over there because there's kind of all these small people in the way. And so in order for Shaq to throw away his trash, what he needs to do is he needs to pass it to the next person, which is kind of the next tallest person. Okay. And then he's going to pass it to the next person because he's not next to a trash can. Okay. And they're going to continue passing it until it gets to me. Okay. And then once it's to me, and I'm the smallest person, so I'm the only person that's the same size as the trash can, I can finally take that trash and throw it into the garbage. Okay. And so what this trash represents, or what that bucket represents, this represents kind of the kinetic energy that's in turbulent flow. Okay. And so in turbulent flow, you have this energy cascade where the energy is passed from the largest scales to the smallest ones, where along the way nothing gets lost just because there's no trash can over there. And then once you get to the smaller scales, then viscosity tends to kick in, and then that's when you can kind of dissipate energy. So remember, there's kind of these 2 separate processes, and kind of the way that you kind of summarize the energy is through Kolmogorov's kind of -5/3 law. Okay. All right. Are there any final questions on this? Okay. So there's no final questions, then we're out of time for today. So I'll see you guys on Wednesday. So please stay safe, please stay healthy, everyone, and have a good evening. All right, so question, is the final still going to be on the 13th? Yes, so we're going to have the final still at the same time that's been scheduled, but it'll be kind of the same format as the midterm. So it'll be basically a take-home final where, you know, difficulty will be roughly the same, and you'll have basically 24 hours to finish it up. It'll be cumulative in that we'll cover things from, you know, from the first midterm, but it won't be absolutely everything. So I think towards the end of this week, I'm going to put together a study guide, maybe in the middle of this week, which will basically tell you the topics that I'm going to expect you guys to know for the final. Yeah. Yeah, the difficult thing is that a lot of the stuff that we do in the later half is really conceptual. So, you know, for problem solving stuff, we kind of have to borrow from the first midterm quite a bit. So final review. So our final review is going to be on our last class session. So that's going to be next Wednesday. Yeah. Yeah, we got to finish up turbulence first before we can do a review. Yep. Sure. Yeah, what's up, Jonathan? To F, let's see. So once you solve for you know, all the other parts, you know, you should get an answer for the velocity. So actually it's there. So basically, you know, considering your answer for part D, you know, is this flow unstable or is it not, right? So basically what you're going to get is that whether you use Rayleigh's criterion or you use Fjordhoff's theorem, you're going to get different answers of whether this flow is going to be unstable or not. Okay, and so based on what you found in part D, you know, which one is more correct. So it's you know, not as it's not as complicated as I'm kind of making it sound. So, you know, once you solve part D, right? Yes. So if you have a flow that's zero, so if is a flow that's zero, is that unstable or is that stable? It's neutral, yes, but it's you know, a flow that stays still. It's not going to. Remember, the way that we define unsteady flows is that there's these small disturbances that kind of grow over time, right? So if you have no flow at all, then there's no way for disturbances to kind of enter into that because it's just going to be completely still, right? So a flow that's zero is kind of just by definition stable. Yeah. Yeah. So then based on that, you know, based on what you found from Rayleigh's criterion and Fjordhoff's, then which one kind of makes more sense? Right? And in the notes, I kind of mentioned which one is more reliable between Rayleigh's and Fjordhoff's too. So all of that should kind of be consistent with each other. Part C. Yes. Yeah, because remember Rayleigh's criterion, you're only checking if there's an inflection point in the flow. So an inflection point is just defined as when the second derivative is equal to 0. So it turns out for a flow that's totally 0, then it's, a flow that's 0, then the second derivative is going to be 0 everywhere. So, Rayleigh's criterion, it's useful in some cases, but it doesn't tell the whole story. Yeah. Yep. Mm-hmm. Question. Yep. All right. See you on Wednesday. All right. So I'm going to end the meeting. So I'll see you guys on Wednesday.